So we're here at the SID Display Week here with the Holst Centre. Hello, so who are you?
I'm Hielke Akkerman from Holst Centre in Eindhoven, the Netherlands.
And who are you?
I'm Pavel Malinowski. I'm from IMEC, Belgium, and we are doing this work together within the framework of Holst Centre.
So what are we looking at here?
So this is a demo of the fingerprint sensor. It's thin film fingerprint sensor, semi-transparent, based on oxide backplane, oxide TFT backplane, and organic frontplane. And this is the technology that enables you to integrate fingerprint sensor in the display. So the long-term roadmap is to have the OLED light emitters and organic photodetectors in the same plane, integrated within one component as a display with integrated fingerprint scanner.
And so when they're talking, the other companies are talking about putting some kind of thing behind the OLED, right?
Yeah.
Is this different?
This is different in the sense that often current optical fingerprint sensors are based on silicon, and here we use printed organic photodiodes as a front plane, which means it's relatively cheap to upscale it to larger device areas, and it makes it a lot more suitable to have a fingerprint recognition over the full display area in your smartphone.
The full display area will be fingerprint.
Yeah, it's fingerprint sensitive, so I can also show it in the demonstrator. I can put my finger basically down anywhere, and you can see on the screen that it will capture it at the different locations. So that has a really big benefit, that you don't have to be location specific in your display of the smartphone on where the fingerprint is captured.
So how is it the accuracy of this kind of fingerprint reader compared to like a separate dedicated fingerprint reader, the ones that are in the phones today?
Yeah, that's another thing, that here we are very close to the finger, to the actual finger. So you have very little distance from your ridges and the valleys to the actual detector. So here we are working in a reflective mode. We are using a commercial backlight unit from a smartphone, and the actual module is directly underneath your finger. And the precision here, we are talking about a 200 ppi demo, so this is 126 micrometer pixel pitch. We also have a prototype of 500 ppi, which is 50 micron pitch, and this is the one that can be compatible with FBI standard for biometrics. So that's the real resolution that you want to target. If you want to integrate it within the display, then you have to have this 500 ppi resolution of the display and the fingerprint scanner. So this is where we have to use some more advanced scaling of the pixel technology.
But how is it possible to? It only works with OLED, right? Or what kind of display?
And mainly intended for OLED display. Yeah.
So how does it work? How can you have an OLED and this at the same time?
So what you can have is these photodiodes have originally been developed for medical applications in X-ray. And there you would like to have a sensitivity to very low light conditions. So if you have an OLED display, it's always a little bit semi-transparent, even if it's not designed for it. So it can have like a transparency of only 1%, for example. But it is sufficient that the OLED is operating, emitting the light, being reflected from the finger, and then being detected behind the display on this image sensor.
So you need this backlight to see something, right?
In this situation, if the photodetector pixels are side by side with the OLED pixels, then you are using the display light as the light source. So then it's about the mode of working. When do you emit light to record the fingerprint sensor? So this is all about the user interface and the interaction. So that the light is emitted when you put the finger on top of the display, and only in that area.
So is it very difficult to align things? So there's somehow yours and the OLED at the same time. You have to align precisely, or It just gets printed out.
The long-term vision that we have is to use photolithography techniques to have patterns, photo detectors next to pattern OLEDs, so that you really have the maximum usage of the area that you have. Because if we are talking about 500 ppi, you have only 50 micrometers that are available, 50 by 50 micrometers for all the colors of the OLED display and for the photodetector. So you don't really have too much space, and you have to figure out how to squeeze everything inside such a pixel.
Is it going to be printed all in one go? Is it one printer, kind of like a printer, you click a button and then the OLED and the fingerprint reader and everything comes out?
That would be a nice machine, yeah.
But
no, in the real situation, you would do it step by step, different colors of the OLED and the photodetector. So here in this situation, the photodetector layer is everywhere on top of the entire surface, which makes it also not as transparent as it could be. But since the photodetector is so sensitive that it works still even with very low luminance from the backlight, we don't need to do the patterning because it's transparent enough. But in the future, if you want to integrate both components together, this might be something that will help.
And you could eventually have some application where one finger launches one app, the other finger launches the other one.
Can be, yeah. It's all about, let's say, creativity of the software developers. Once you have the possibility to have the fingerprint anywhere on the screen.
Could this be a big issue for all these borders and security people that are buying all this stuff?
No.
Why would they want to have this, what they have now?
So if you look at what you get now at immigration, for example, on fingerprint scanners, that's all based on also a reflective measurement with small sensors. Use bulky prisms, for example. And this is technology because if we do it on plastic foils, we can make it as thick as, say, 60 to 80 microns. And then you can easily integrate it in all kinds of surfaces, and you can make it also larger. So here we can do, for example, 4 fingers at the same time, which is also what you use at immigration. But the form factor is a lot thinner compared to the current fingerprint scanners.
Also for robustness, this can be done on foil substrate, so you are not dealing with the glass components, but you can have something that is kind of seamlessly integrated into some molds and more freeform objects. So you can imagine that a full palm print scanner is, for example, in a police car. So you can do the full palm print scan directly in the car when you catch somebody that you want to register.
All right. So what's next? Some companies are going to take this and make it?
Yeah, that's the plan. So we have a lot of industrial partners. Some of them are in the process where we transfer this technology for mass production. That is still a bit for different applications though, for medical X-ray images, where you use the same kind of technology for medical flat panel detectors. But we're also looking into companies that can do this in mass production for fingerprint scanners, biometric, into all kinds of commercial products.
So the nice thing is that we have these technology blocks that we can integrate, and based on the request from companies, we can go in the direction of, for example, folding this fingerprint scanner around handlebar or door handle or other objects, or integrating it with the display, or going to large size, or even higher resolution. So it a little bit depends on the demand, but we are ready to accept these challenges.
Yeah.